Hi, everybody. Welcome to week one of Robotics Engineering Weeks. Today's topic is precision motion control for robotic systems. My name is Steve Crow. I'm the executive editor of the Robot Report. Thank you, folks, for joining us today. The topic should be pretty clear, I think, by the title of today's talk, but you'll be learning about how the latest technologies and products that support the development of advanced precision motion control systems are allowing for new capabilities, new applications, and entry into new markets when it comes to robotics. But before we get into that, in today's presenter, there are a couple of housekeeping notes that we need to go over first. You should see a variety of boxes on your screen on your webinar platform. Just know that you can move those boxes around. You can resize them. You can do all sorts of things to customize your viewing experience today. A couple boxes that you'll want to make note of. The resources box has the slides of today's webinar in there. There's also a Q&A box where you can ask questions to today's presenter. The last 10 minutes or so, 15 minutes will be reserved for our Q&A session. But feel free to type those questions into that Q&A box as they come to you so you don't forget. If you're watching this on demand, just know that you can also ask questions, which we will forward on to the presenter as well. So just make sure you guys do that. And if we don't get to all of the questions, again, we will pass those along to today's presenter. And the recording of today's session will be available on demand at roboweeks.com. You'll also see it promoted in some of the Robot Report newsletters and social media channels as well. So if you're looking to rewatch this or share it with one of your colleagues, there's multiple ways that you'll be able to find this webinar on demand. And if you happen to run into any technical issues during the webinar, the most common resolution to the problem is typically refreshing your browser. You won't have to relog. You shouldn't have to relog in anyway. It should just bring you right back into the webinar. But if any issues persist, please reach out to us through the Q&A box. Our producer on the back end of this, Lindsay, she'll make sure to resolve your problems as soon as she can. I do want to thank today's sponsors for supporting today's webinar. It wouldn't be possible without their support. Harmonic Drive, PBC Linear, and Bokers. You'll be hearing from Harmonic Drive here in just a minute. I just wanted to let you know they'll also be exhibiting and speaking at our upcoming Robotics Summit and Expo, an event that runs May 1st and 2nd up in Boston. This event brings together 5,000 plus folks from the commercial robotics development ecosystem. It's going to be 2 days of learning, 2 days of networking, really designed to help robotics engineers overcome the technical challenges that they face when developing commercial robots. So it's going to be a great couple of days. You'll find Harmonic Drive in booth 101 with its latest motion control products to, again, help solve your robotics engineering challenges. So now I would like to introduce today's speaker, Mr. Lee Ginter, a sales engineering manager at Harmonic Drive. He's responsible for sales and application engineering activities in the central US region. He has 30 plus years of experience in the motion control industry, offers a wide set of experiences and expertise, assists Harmonic's customers with developing the right precision motion solution for their particular business need. You can learn more about Lee. You can connect with Lee through the speaker bio box that hopefully everybody sees in their console. But without further ado, I want to hand the reins over to Lee. Thank you so much for being here as always and for lending us your time and your expertise.
Thank you, Steve. Glad to be here. All right, let's get started. Again, my name is Lee Ginter, Sales Engineering Manager with Harmonic Drive. I have been with Harmonic Drive for 10 plus years, and I have over 30 years experience in motion control industry, working for various manufacturers in linear motion, servo drives, controls, and so I've seen a bunch of different applications and glad to be involved in the robotics market. Let's get started. Here's a quick agenda. We're just gonna, this is gonna be technology strain wave focused, but I just want to do a quick introduction on, who and what Harmonic Drive is. We'll talk about robotics and motion control, how it's a natural pairing. We'll do a strain wave technology overview and, why strain wave has become the de facto technology standard in the robotics market. We'll go over some features and benefits. We'll look at some robotic application examples and some various harmonic drive strain wave solution variations, and then finally design trends that we see for robotic joint designs. All right. For some of you that aren't familiar with harmonic drive, we are, the original inventor of the strain wave gear technology. The product was invented by an American inventor, 60 years ago. Walt Musser was his name. We're obviously the market leader in precision motion solutions, over 60-year design, engineering, and manufacturing experience. We're a global company with R&D manufacturing in the US, Japan, and Germany. ISO 9001, AS 9100 certified, and a variety of applications. You can see a couple of pictures here, aerospace, space flight, satellite. Those have been long-standing applications for us. Also semiconductor, surgical industrial robots, and machine tool, to name a few. Globally, as I mentioned previously, there's three main R&D manufacturing locations. In the US, we are located in a northern suburb of Boston, Massachusetts. In Japan, there's several factories. Most of them are located in the Nagano prefects, which is about a 4-hour train ride from Tokyo, approximately. And then the other company that handles our European business, Harmonic Drive SE, is located in Germany. They are located approximately half an hour from Frankfurt. So this gives us local, regional customers' ability to develop special need products with speed and quickness to meet the market demands that we see. What's driving the growth in robotics? And from a high level view, we see a few things going on that are driving these mega trends. Demographics, life expectancy is getting longer. There'll be over 1 billion people over 65 years old in another 8 years or 6 years. The need for increased medical services and robotic devices will continue to grow. Technology, rapidly developing, utilization of AI is enabling, huge growth in robotics right now. And 5G will help accelerate Internet of Things and widespread consumer, industrial applications. And the last one the last mega trend we see is urbanization, and that's 2/3 of the global population are projected to live in cities, creating more mega cities as well as medium-sized metropolises. So transportation, logistics, ground and air become a challenge. And robotics will, I think, help serve this need. So with all this robotics growth that's forecasted, there's many studies out there that are showing the growth, the short-term and long-term growth, but the need is for precision motion control. One such report that we pulled up shows the compound annual growth rate of about 16% between now, 2024 and 2029. So if the market size is about 45 or 46 billion now, it's projected to get up, towards 100 billion by 2029. So that's a pretty aggressive growth. This is interesting. This one study showed the fastest growing market is North America. So that's interesting to know. And Harmonic Drive, along with all the other robotic suppliers, are going to have to support that fast growth. The largest market is still Asia Pacific, according to this. And here's some of the the big industrial robot guys that are all the big players in Fanuc, Kuka, Yaskawa, ABB, Denso, and there's obviously many others. The use of robotics in every industry is increasing, and demonstrated by this aggressive growth year over year. And due to the demand and adoption of robotics technologies across automotive, healthcare, logistics, manufacturing, that's where a lot of this demand will come from. All right. So why is robotics and precision motion control, why are they a natural pairing, hand in hand? A lot of this is pretty straightforward and obvious, but robotics focuses on precision, controlling the movement of various components. The most important part of any robot is its motion and its ability to be controlled precisely. Requirements for advanced motion control algorithms and components have increased significantly and will continue to do so. Robots of all types have to interact with physical objects, uncertain properties and positions, the need for precise control to avoid unforeseen errors, such as backlash is a major challenge. And last but not least, strain wave technology, developed by Harmonic Drive, offers zero backlash and is used in a variety of critical applications for precise motion control. So now we'll get into, the strain wave gearing technology, what it is, how it works. I have a few slides on that, and then we'll have a video shortly after that to show how all these three main components interact. The first element of our harmonic or our strain wave gear is the circular spline. The second element is the flex spline, and the third element is what is known as a wave generator. The wave generator is essentially it's an elliptical steel plug with a special thin race bearing wrapped around it. So when that bearing is inserted on top of this elliptical shape, it conforms to the shape of the ellipse. And that's the critical driving element of a strain wave gear. The flex spline is essentially either a steel cup or a hat shape, thin wall steel cup with gear teeth on the outside of it. That the cup is torsionally rigid but radially compliant. So when the wave generator, well, we'll get to that in a second, but so there's teeth on the outer rim, on the outer diameter, and when the wave generator is inserted inside the cup, this thin wall, flexible cup now conforms to the shape of the ellipse. And then the final element is what we call the circular spline. It's a rigid circular ring with teeth on the ID. And the number of teeth on the circular spline are 2 more than the flex spline. And so basically, when all these 3 parts engage, you'll have a minor and major axis of engagement, and at any given time, there will be over 30% of the teeth completely engaged. And let's just talk about some of the features and benefits. Then after this, there'll be a video where you can see how the interaction of all those 3 components work. So features, benefits, Harmonic ear is inherently zero backlash, and it has high positional accuracy. Positional accuracy is typically less than 60 arc seconds, with repeatability of plus or minus 5 arc seconds. So very high repeatability. It's compact, and that compactness gives it high torque density. It's inline configuration with hollow shaft capability. The Harmonic drive is inherently a high reduction ratio, and those ratios vary from 30:1 for some of the smaller sizes and go up to 160:1 ratio, all in a single stage. And no matter what ratio is applicable for an application, the size of the Harmonic ear remains constant. It's just the number of teeth on the flex spline and circular spline change the ratio. The Harmonic, the strain gear is inherently backdrive capability. Has backdrive capability, and that backdrive torque is published. And the most important thing, and we'll talk about that a little bit later in the presentation, is the strain wave gear also has design flexibility to meet each designer's performance, accuracy requirements, and dimensional requirements. So now we're next. I'm just going to play a quick little video to show you. Sometimes it's easier to see how these 3 parts interact. It's very unique technology. So let's play the video.
High-precision, zero-backlash harmonic drive gear component sets are key to the performance of our gearheads and servo actuators. Harmonic drive component sets consist of only 3 precision components: wave generator, flex spline, and circular spline. The wave generator is the driven or input element of the transmission. A hub having an elliptical shape is fitted within a special thin raced ball bearing to create the wave generator. The flex spline is a robust, torsionally stiff, yet radially compliant component with external gear teeth, capable of reliably transmitting high torque loads. The circular spline is a rigid ring with internal gear teeth. The circular spline has 2 more teeth than the flex spline. When inserting the wave generator into the flex spline conforms to the elliptical shape of the wave generator. Rotating the wave generator creates an advancing waveform on the flex spline. When assembled with the circular spline, tooth engagement occurs at each end of the major axis of the ellipse, and up to 30% of the total number of gear teeth are simultaneously engaged. The rotation of the wave generator causes the flex spline and circular spline tooth mesh to move around the circumference. Since the flex spline has 2 less teeth than the circular spline, Rotation of the wave generator leads to a relative movement between the flex spline and the circular spline. Harmonic drive component sets, gear heads, and servo actuators are used wherever zero backlash, extreme precision, and high reliability motion control is required. Harmonic Drive, advancing the technology of motion control through innovation.
Excellent. Moving on. Hopefully that video helped some of the audience. Why is the strain wave gearing de facto standard for high precision robotic motion control? So the trends we're seeing in robotic arms, that there's several of them, but some of the important ones are, more people want more options for end of arm tooling and grippers. They want increased performance, more sizes, types, functions, localized control functions, torque, strain gauge feedback. So basically all that means, smaller and increased capabilities. The performance requirements typically are positional accuracy of less than 100 arc seconds, repeatability of less than 10 arc seconds, ideally high moment stiffness, high torsional stiffness, capable of complex motion paths, low profile and high performance requirements. So the applications driving new requirements, and of course there's traditional industrial robots that have been around for a while, but that there are newer applications driving, and many of them have new requirements. I'll touch base on a few of these. In the surgical medical robotic arm arena, these particular applications are looking for dexterity, precision, maneuverability, safety, compactness. And mobile logistics robots, efficiency, impact loading, compactness, and weight. Another, big application that is getting a lot of publicity now are humanoids. And, some of their requirements are form factor and weight, maneuverability, safety. And the cobots have been around for a year, and that market continues to grow as well. Torque sensing, safety requirements, cost. So, a lot of these have similar demands and requirements. And, the strain wave gearing typically is a great solution and meets many of these requirements. So talking about gearing variations, there are many form factors of a strain wave gear, and a lot of these different form factors really comes down to the designer of the robotic joint. What are the resultant design requirements? Does that designer have physical constraints, dimensional, weight, inertia? Do they have some performance requirements, accuracy, repeatability, dynamic response? And what kind of life requirements, duty cycle, e-stop capability, mean time between failure, and then the last one's environmental as well. Are there any temperature concerns, corrosion resistance? Is this going to be in a vacuum? Are there certain IP ratings? So strain wave gears need to be able to adapt to, a lot of these design requirements that these robotic joints will have. So there's many different form factors to help meet those. And then within each form factor, these they can be modified slightly or significantly depending on what the application requires. And so here's just a few cross sections showing you some variations of strain wave gearing. And from the left, that's what we call a wine glass design. The one to the right of that is a Silcat design, which allows for large hollow bore applications. The one to the right of that is a standard cup style. The one to the right, which actually has the pitcher in it, is a newer variation for us, and it's called a lightweight design. And then last but not least, all the way on the right, is a compact design. So for very tight axial spaces. And, a product overview, this is kind of important to show because, there's building blocks of strain wave gearing. And, the most basic elementary is what we call a component set. And the component set is exactly what it sounds like. It's the three components: the circular spline, the wave generator, and the flex spline. And when designers typically will choose a component set if they need maximum flexibility. The component set will require you to design a housing and a bearing support around it, but it gives you the most flexibility. If a design, the footprint or, the overall dimension flexibility is not that critical, it might make sense to look at a pre-engineered, what we call gear unit. And the gear unit is basically a component set in a housing with a integrated output bearing, which is typically a cross roller bearing. So this gives a compact, completely housed gear unit or gear head that can be dropped right into the application. And then the higher level design would be what we call an actuator, and this would incorporate our harmonic, a strain wave gear, a servo motor, an encoder, a output bearing support, and in some cases an integrated drive built into the back. So these actuators are perfect if they have less flexibility than these other groups, but if the performance and the footprint meets an application, all the engineering's done already. So these are excellent choices for applications as well. I want to the next couple of slides, we're going to go over what we've seen, and I've personally seen some design trends specifically for some of these newer robotic markets like humanoids, cobots. We've seen some requests and requirements for lightweight. I mean, that's everything needs to be lighter weight. And specifically, if we're talking about like a humanoid design, those are typically battery powered. And, obviously lightweight helps preserve battery life and, allows torque to be reduced at the extremities, which, saves on battery life. So I'm just showing here an example of a lightweight component set that we have. It's called our CSG series. And essentially, it's 30% lighter than our standard component set. That's significant weight savings. It also has the same performance as a standard unit as well. And there is a large hollow bore option available with it too. This comes in, this particular product comes with two options: a standard flex spline bore, and then a larger, what we call a big bore option. The next trend that we see is large hollow shaft gears as well. This particular unit, this is a gear unit, so it's a component set that has a housing and a output bearing. You can see here that this is the hollow bore. The difference between the OD of this gear unit and the ID is it's very compact, and it allows for, you know, this is I envision this, and the applications that we've seen apply to is a lot of end of arm tooling where you need the pass cables, you know, pneumatic tubing, sensor wires. This particular product line allows some flexibility and some cable management as well. And then the last trend that we see is integrated servo drive. So basically, this is our servo actuator with an integrated servo drive. I'm sorry, I got sidetracked for a second. So basically, this product line is our standard servo actuator, but what we've done is we've integrated a servo drive into the back of it, and currently the communication interfaces can't open, but we are working on EtherCAT and expect to release that shortly. So you basically have all the attributes of our standard servo actuator, but now you don't have to worry about running cables out to a separate amplifier, and you know, what we've also done too is added a dual absolute encoder to the system as well. So there's an encoder on the motor rotor for commutation, and there's also an absolute encoder that is connected to the output side of the unit as well. So you have it's a dual absolute encoder, integrated servo drive. So this is allowing some designers as well to simplify their design, simplify the cable management, and you know, you don't have the flexibility of starting with the component set, but here again, this design is, you know, if it meets the footprint, it's complete, and eliminates a lot of the engineering that goes into designing an actuator yourself. That's pretty much it for that, and I think that might even be the end of the presentation.
Awesome. Thank you, Lee, for doing that, as always. So we are in the Q&A portion of the event. So folks, if you have any questions that come to mind based off some of the things that Lee got into there, maybe there's something that he didn't get into that you're curious about learning about while we have him here, make sure you drop your questions into the Q&A box that you see in your webinar platform. And again, just a reminder for those who are in the future listening to this on demand that you can still ask a question as well, which we can send to Lee and the fine folks at Harmonic Drive after the fact. A question, Lee, that came in asking about torque sensing. Anything that you can share with us about torque sensing with harmonic drives?
Yeah, that's another hot topic. Great question. Currently, Harmonic Drive, we don't have anything to share, but I can tell you that we are working on having solutions that will implore or implement a strain gauge and have some type of torque sensing. We see that demand coming from multiple markets right now, and it's getting a lot of emphasis in our R&D department. So more to follow at this point. I don't have a solution to discuss, but that will be. I envision that being a solution that will be offered both on a component set level and then further down the road on our actuator and integrated actuator product line.
And I imagine, and again, I'm not trying to press you too much on this, but I would imagine something like a torque, torque sensing is used, and you went through all these different applications where you guys are playing in. Torque sensing is something that goes into many different types of robotic systems and different applications.
That's correct. And as of now, our customers are adding that functionality themselves. So, as we go forward, everybody's looking for a tighter integrated solution. And, they're coming to us now asking, what can Harmonic Drive do to tightly integrate that into our product? And, we're taking the task on, and more to follow.
Yeah. So there's questions from Joseph. Joseph, we're not going to get into the timeline any more than what Lee has just said. So we'll make sure to connect you after the chat here is over, if you're interested in learning more about what's coming from Harmonic Drive. A couple of questions here, which I think are very interesting. You did mention some of the lightweight products that you have, and ensuring, I think you said 30% lighter, but also trying to maintain that same performance standard. What are some of the trade-offs for using that lightweight design?
Yep, another good question. And there potentially are trade-offs. First off, the lightweight design, masses, we're removing mass from the unit. And so there's like two main potential areas to pay attention to if you're using a lightweight gear. And the first one is, and we're talking about a component set. The first one is the customer's mating parts. So they'll purchase a lightweight component set, and now they're charged with designing this into their robotic joint, and there's mating parts that made up to our gear and the joint, and because we're removing weight, in this case from the circular spline, there's some reduced radial stiffness of that circular spline. So a lot of design attention needs to be, even more so than the standard unit, needs to be make sure that that circular spline is piloted correctly, and the customer's mating parts they're designing need to be rigid and robust. Just some extra care has to be taken when integrating a lightweight into the design. And the other thing to pay attention to is I mentioned in the lightweight, there's a large or a big bore option, a larger bore option. So that larger bore is in the flex spline. And so when we increase that bore, the maximum torque, and when I say maximum torque, I'm not talking about like repeated peak application torque. This would be like a momentary e-stop type of torque, is now limited by the transmission torque of the bolts, fasteners, and dowel pins in that unit. So you'll see with like a large bore lightweight gear, like the momentary peak torque will be slightly reduced from the standard. But from a performance level, accuracy, repeatability, those all remain the same and unchanged.
Are you in some of the lightweight products? Are there different material options, or are you guys, making them lightweight by actually removing the material with the
Yep.
bigger bore that you talked
Yep.
about?
Good question, Steve. No, it's our standard materials. So the lightweight aspect of that is achieved by removing mass from the standard material.
And every robot's trying to get lighter,
Yeah.
stronger,
Yep.
faster.
Exactly. Yep.
Are there more specific, are there certain applications or certain types of robots in particular where you're Harmonic seeing this, more of a demand for these lightweight versions?
Yeah, I would say, cobots and humanoids. Your traditional industrial robots, they're big metal. They're powered by, high AC main supply. Um, any application now going forward that will be what I call mobile, meaning it will be battery powered. There'll be an increasing focus and demand for lighter weight. And obviously, for example, a humanoid, it has battery packs on its back, and it needs to be as lightweight as possible to help preserve that, long life of the battery.
I'm always jealous when I talk with you guys. You guys see all these emerging robots that are coming down the pike. Where folks like myself, I would just love to geek out over these humanoids. But
Yeah.
what kind of challenge is that for you guys from an engineering standpoint? Just because this is humanoids have been around for some time, obviously, but really for research purposes, right? At universities and labs to study robotics and study, legged locomotion and such. Now these humanoids are being developed in hopes of being able to perform real world tasks, whether it's at a warehouse, maybe at a manufacturing plant, both. That's a whole different ballgame, right? But and I know you can't get into it too much, but from an engineering standpoint, I mean, how challenging is that to try to hit these different benchmarks and performance benchmarks, which are changing for these humanoid developers very, very quickly?
No. Yeah, we've been asked to, basically, Steve, reduce weight more, and there's reaching a point now where you only can do so much if you still want performance. So we're dealing with a fine line of, well, if you give up too much weight, or change some other attributes, you start to cross a line of, diminishing return, because now you're starting to give up performance. So the challenge is to, try to meet the customer's requirements, and then also a driving force behind this too. And when you start talking about some of these companies, that these supposedly, if you believe what you're hearing and seeing, there's could be some very large volume of these robots that some of these companies are trying to make. So the other challenge there is to, make sure that, you have robust production and manufacturing, local manufacturing to support those types of customers.
Yeah, I mean, I don't even know what the average unit would be as far as going into a humanoid, but a dozen, probably more so than that. Yeah, lots of opportunity.
In many cases, more. Yep.
Yeah, right. Another question, and folks, we got a few more minutes here, so if you have any questions for Lee, make sure you get them in now. And again, if you're listening to this on demand, feel free to fire away as well, and we'll pass it along to Lee and Harmonic Drive as we get them. We've talked a lot about customizations and modifications. Can you just sort of recap some of the design modifications that are possible using the different component sets?
Yep. So, and that's a good question. Let me start off by saying, no application or every application is different. Every customer's requirements are different. You know, 70 close to 70% of the products that we produce are what we consider special. And that's a pretty high number. So, you know, what is a special? And, you know, that special can be a mechanical, you know, a mechanical change. A special is anything, let me back up. A special is anything that we don't consider you know, a core or a standard catalog item. You know, we have products we put on our website and our catalog that all have standard dimensions. So a special would be something that deviates from that. And you know, there's mechanical modifications and then also performance modifications. I would put those in two classes. Mechanically, you know, there's the three parts of a strain wave gear. Circular spline, that could be, you know, whole pattern changes, which is pretty easy for us to handle. And the flex spline, again, that could be a whole pattern change, which is pretty easy. The most common mechanical variation request that we get is with the wave generator, and that would be the different bore to accommodate either a different motor shaft diameter or some other type of input drive mechanism into it. And then from the performance standpoint, you know, some of the most common requests that we get are, you know, someone wants lower backdriving torque capability, and that's really prevalent in you know, robotic arm applications that are manually being positioned by a user. For example, like a cobot, you know, doing a teaching, you know, you're in teaching mode and you're trying to move the cobot arm around. And another one would be like a surgical robot where, you know, the physician or the nurse is in there trying to position this arm. You can't have, in those applications, you know, gearing in the 5, 6, 7 joints of the arm that are really difficult to position manually.
Yeah, you were saying the learn by demonstration mode. Is that what you were saying, right?
Yep. They call it teaching mode, but yeah, learn by, yeah, everyone can call it something different, but yeah. And then, you know, another performance might be someone wants a lower starting torque as well. That's another big one. But, you know, when you start messing around and lowering backdrive torque and starting torque, you know, it's a give take benefit because now, depending on, you know, how low or how much modification the customer wants, you may give up something else. And, you know, for example, if we're talking about performance and low backdriving torque, you may give up some torsional stiffness of the gear unit. So, you know, you have to try to balance those asks and, you know, and be realistic with, you know, the performance benefit, you know, that you end up with.
So it doesn't look like we have any more questions. Thank you to those who sent your questions in. And again, if you are rewatching this or if you're watching this on demand, you know, oh, looks like we just got a question about exoskeletons and back drivability in exoskeletons. Is that another example?
Absolutely. And, you know, in exoskeletons, it's lightweight, it's compact. Compactness is another big, yep, back drivability. That's another key feature as well. Yep.
Stein, thanks.
And you
for
know
that.
what? In some of these applications that want, you know, if the low backdrive torque is highly desirable, you maybe a slight loss in torsional rigidity of that gear, doesn't matter so much. So, each application is discussed, and, you just got to try to come to a happy medium. But yep, absolutely.
Yeah. So I think we'll wrap up there, but Lee, maybe just some closing comments from you, about recapping all that you talked about here. And maybe there's somebody in the comments is asking about diameters of the different products that you talked about, but also can you point people where they can learn more about what you guys are doing at Harmonic Drive?
Yep. Thanks, Steve. Yep. Our website is the best source of information. That's www.harmonicdrive, one word, harmonicdrive.net. And on that website, you can see all the various, products, the component sets, the gear units, the actuators. We have some videos. The video you saw is also on our website if you wanted to view that again. And then also, you can search, depending what area you're from, you can search and define your local sales engineer. And, all of the Harmonic Drive sales engineers are degreed engineers. So we're all heavily involved on the application side, not just the sales side, but the applications side to help direct you to the right solution. Again, we have a complete factory with R&D engineering, application engineering, design engineering, all located here in the U.S. And again, that facility is just north of Boston, Massachusetts. And I think that's pretty much it, Steve. I think that's a quick summary.
Yeah, great place to wrap up our talk today on precision motion control for robotic systems. Again, if folks are tuning into this on demand for the first time, if you're rewatching it and something sparks a question based off what Lee was saying, maybe there's a question that you have that he didn't get into, just know that you can ask questions on demand that we will then send to Lee and the fine folks over at Harmonic Drive as they come in. So don't be shy, folks. Take advantage of their expertise while you're here. So thanks again, Lee Ginter, Sales Engineering Manager at Harmonic Drive. Thank you, man, for lending us your time today.
Yep, absolutely. Thank you for having me.
Yeah, anytime. Also want to thank the sponsors, of course, Harmonic Drive, PBC Linear, and Bokers for sponsoring today's event. Wouldn't be possible without their support. Do want to point out that if you have more questions about Harmonic Drive, they will be exhibiting and speaking at our upcoming Robotics Summit and Expo. It runs May 1st and 2nd in Boston. The event is an event for commercial robotics developers. There'll be 5,000 plus folks from that ecosystem there for 2 days of learning, 2 days of networking, and really 2 days to just push the commercial robotics industry forward. Obviously, motion control will be a big focus of ours at the show. So if you have any questions for them, you'll be able to find them in booth 101. They'll have their latest motion control products there that can help you guys solve your robotics engineering challenges. And again, I want to thank everybody for tuning into this today. If you enjoyed this webinar, if you want to share it, as a reminder, it will be available on roboweeks.com. You'll also receive a link in your email that you can use to forward it to someone you know who might enjoy this as well. So on behalf of everybody at the Robot Report, my name is Steve Crow. Thanks so much, folks, for tuning in. Hope to see you again soon.